So the last topic of this intensive course is about IIR filters. And let me go directly to the welcome. I just started, so perfect timing. So actually I'll go through the kind of the brief introduction what we are talking about now. So it's a filter design 2, meaning IIR filters, and how you recognize an IIR filter from zero pole plot Argand's diagram. Well, the zeros can be anywhere, for example, there, but then you have the poles. If all the poles are either at the origin or at the same place as your zero, then it will be FIR filter. But IIR filters would have these pole locations basically on the pass band inside of the unit circle and on the pass band. Think of the system without these first. In this case, we would have the those notches on those 3 points. So like that. And if this was an FIR filter, then it would probably look something like this. The amplitude response, I mean. So amplitude response of this system would look like that without these poles. But since we have the poles somewhere else than on the origin, oh, wait a minute, I need to put this one on the different place. Something like that. But since we have the basically that amplitude response is also can be marked like this, divided by e to j omega distance to poles, meaning that okay, if you have a 0 point in a unit circle, then it gets the 0 amplitude response on those frequencies. But then if you are close to a this pole, for example in here or there or here, that would increase the so this would be less than 1, meaning it's actually giving some local gain on these angles. Maybe something like this. So you would get local gain due to those pole selection pole locations. And basically that's what usually those poles are for. They will basically give more stop and attenuation. So stop and attenuation gets better, and also you can have the pole locations so that you will get, say, relatively flat the pass band. Okay, so that's one way of looking at it. However, the design of these IIR filters is almost never done in a zero pole plane, but with some, say, other methods like modeling an analog system. On analog filters, we have this the Salenki filters. Salenki low-pass filter would look like something like with some gain. Okay. Right. Oops. That's a Salem-Key low-pass filter. Does it look familiar? It should ring your bell. Okay. So you know that, okay, your the eighth of eights is, well, something. For low-pass filter, I think something like S squared plus AS plus B, something like that. In that form, second order low-pass filter. I'm not sure about if this is plus or minus, but anyways, you should know that. Okay, so anyways, we can always model this filter. If there is a the h of s, you can do so-called bilinear transformation by setting s equals 2 over t s z minus 1 divided by z plus 1. That'll do the transformation from analog domain to digital domain, but with a distortion of, it makes actually quite a lot of, it's kind of violent operation, since it basically takes the plus and minus infinity on the frequency of the S plane, where you have j omega here. You take this and turn it into unit circle. So that's what the transformation actually does. So it means that it's really doing some serious distortion of the frequency space. But saying that it also is a transformation where you can still basically define the cutoff frequency, the flatness of the band pass, and then attenuation on the stop band. Okay, so but anyways, that's one way, kind of classical way of doing the IIR filter design. So it's bilinear transformation. Oh, right, but you don't need to actually do that one in reality, since the MATLAB has these generators for different filters that you can just use it, and it gives one of those classical filters like Butterworth. Okay. Butterworth, Chebyshev, Bessel elliptic. Okay, so that's kind of one way of doing it. Another way would be, so this is first bilinear transformation. Another method of actually doing this would be some optimized methods. Where you basically first have a cost function is something like the integrated difference of the desired or modeled, the desired transfer function, or actually e to j omega, and minus your model e to j omega, and actually do a minimizing of this by changing your model. Okay, that's the principle. that's which is behind of some of these optimized methods on FDA tool of MATLAB. They are these least squares methods. That's basically optimizing the filter coefficients. Okay, it's not that hard actually in practice to do your own optimization, but why the bother since they are already the design the functions to do it. Then third one, basically this is a special case, a stop band notch filter. Stop band stop notch filter. Yeah. Band stop notch filter is a nice practice actually. A filter you can design by pen and paper. So think of a signal spectrum where you have just some obnoxious sound somewhere. So it's like 440 hertz and you want to get rid of that. I hate note A. Okay. So Nyquist frequency here. So basically what you would do is to take this frequency of whatever that is, our noise frequency, and the corresponding angle, the omega n, and put a notch here, meaning the amplitude response goes to 0 at that point. Ha! Problem solved. Kind of, sort of, but it looks ugly. Oops. It's not asymmetric, and it's quite wide band. However, you can improve this one by adding, well, just like here. You actually add some gain by putting a pole close to the unit circle on the same angle and the complex conjugate pair. What this one does is it will make this one almost unity gain. Okay, think of a point here. All both the pole and 0 are on the same distance, meaning this ratio is 1. Okay, and actually when you get distance A here, so this is actually roughly minus 3 dB width, half width. So you also get the control of the width of this filter. Well, simply A here is the F3 minus 3 dB divided by Fs times 2 pi. Just linear scaling this value to the complex angle. So after this, you get the amplitude response of this filter is much better in sense of a filtering properties. So it has almost flat passband, controllable the bandwidth, and the controllable the notch frequency. One more detail. Okay, we expand this part or that part there. Okay, let's put this one. So that 3 dB point, where that one actually comes from. Well, if this distance is A, and this distance here is also A, that distance is square root of 2 times A, which means on this ratio, you have the distance, I'm losing the pen here, J omega, distance from E to J omega minus ZK, and then E to J, oh well, Z1, let's put it this one, or Z2, this is Z2, P2 minus P2, okay. And the other one, well, if you are here, basically the distances there are about 1, the ratio is about 1, okay. So, okay, so this upper distance is A, and the lower distance is square root of 2 times A. So yes, 1 over square root of 2, so it means that the amplitude is there, minus 3 dB. Right. So it's, directly distance on the S-plane. All right, so, okay, let's take a closer look at these things by, we do it on the reverse order. First, take a look if this one works. Band stop notch filter. Can we actually take off that sound 440 hertz from the signal with this method? Maybe. Then we'll take a look at how to design, use the tools to design this minimum order, the classical filters in digital domain. If you want to, you can always use the FDA tool for the designs. All right. So, I'm working on an octave again. So let me start by creating some things to work with. So first, sample rate for the system. Well, we haven't used 8,000 yet. So 8,000 samples per second. There. Then the make some noisy signal. Oh, by the way, which part is noise and which part is signal? Well, it's up to the user to decide. Now I just decided that, okay, my sinusoid is the noise part, and this random numbers are the signal part. Ha ha. Could I do something fancier? Yes. Let me do some fancier things. Yes. So SNO equals say 0.5 times sine of wait a minute. Let me first make the index sampling index vector 1 over fs to 1 second long sample time vector using that sample rate. Yes. Sample the Huh? Yeah, 1 divided by, yes, thank you. Okay, so That's the whole thing. Good. So those are the samples, and then the signal itself. Let's put there the say 0.5 times sine of 2 times pi times 430 hertz times t plus, okay, 0.5 divided by 3, haha, of sine of 2 times pi times 3 times 440 hertz times t. See what I'm doing actually here. I'm actually making a third harmonic for that 440 hertz. And you know, when you add it 1 over 3, it means that it would resemble a little bit like square wave. A little bit, not much. Adding more of those components, it starts to sound like a clipped distortion. All right, but I want also some noise, 0.1. Oh, okay, I'll just leave it like that. Add some noise to it, SNO plus 0.1 times round n size of TT. I have so big font that it doesn't fit into one. Well, it might be actually a good idea also to keep the noise and SNON. Good idea to keep this noise and signal separate, just for fun. All right, so this one sounds like okay. Sounds like that. And now I decided my 440 hertz is the disturbing part. In reality, you would do the spectral analysis to find what is the disturbing part. But anyways, I'll just jump into conclusions here. So 400 filtering out the 440 hertz signal. It starts by defining my notch angular frequency, so that omega n 2 times pi times the notch frequency divided by fs. So this is the complex angular frequency. There, of the sampled signal. Next, we will put a pair of zeros on that angle. So my zeros are actually exponential of j semicolon minus j, so complex conjugate pair, times the angle omega n. There. So those are the coordinates. Quite close to the angle 0. Well, next we would then define the what we would be like to have as the minus 3 dB half width. So half width of the filter. Let's see, 440 hertz. Then we don't want to mess up with the harmonics at least. So let's put just for fun 50 hertz there and see what happens. Oh, is this well? Yeah, 100 hertz to make a point, since when you put it closer to the unit circle, then it doesn't show up that well on the zero pole plane. Okay, that's in hertz, which means that our A, okay, now a small problem here. Let me call it O instead of A. Is 2 times pi times that frequency divided by fs. Okay, so this is the half width as a complex angle or distance. Yes? Yes, half bandwidth. So basically, you're setting this half band is right there. So you have the same distance on this way, which is the angular distance, but yes, distance, still distance here. Nice trick. Complex angles on this the complex plane, you just multiply with the radius and you get the distance. Right. Or if you have radius, then you can make it to the corresponding complex angle, meaning corresponding the frequency. It's a scaling. All right, so now we have that one, which is my 1 minus radius. So my radius of this pole is actually 1 minus O. And the poles are on the same angle as the zeros, so I just take this radius times z. So poles at the same angle as zeros, but different radius. And now I can actually do the z-plane of z and p to see. Sorry, I had an extra comma there. There we go. See, I got a zero pole plot there. And let's see, now I should be able to. Can I zoom this? Ha! Yes, I can zoom. All right, so same angle, and that distance is actually directly proportional to our half width. Okay. Good. So the corresponding filter coefficients when we have zeros and poles. We have done it a couple of times. So the B are the polynomial coefficients of the polynomial defined by these zeros, and A parameters are the polynomial coefficients of these roots. Good. Those are the filter coefficients. Done. Now we have a filter. And basically what I can do, let me put the figure 2 and say frequency response of B, A, 1024 points and sampling. Great. Wow. There we go. So we have a flat unity gain pass band, and we have the well. Don't worry about this. Say phase response is highly nonlinear phase response, of course. But on the other hand, we have only second order system to do it. So it's very cost efficient filter if the phase is not that big deal, as in basically in audio signals, we don't have that big deal on the what is the phase shift. Or if we are doing post-processing of the data. Okay, so basically that requires a little bit of explanations. Okay, so post-processing. So this far we kind of have considered the phase response as linear. That's good for say data transfer, meaning real time signal processing of data transfer. So this okay, transfer. Then we have the nonlinear, for example, for audio. But I haven't told you anything about yet about the zero phase shift. Zero phase shift filter, and that's basically the post-processing. Meaning that, well, not real time. We are doing some post-processing right here. But in reality, basically, those digital filters are, generally speaking, those are real-time filters. Anyways, zero phase means that if you first put the system through the H of Z, then basically reverse the time, put it again through the same system, then reverse the time again. What happens? Well, if you have a phase shift, here in this filter actually have the negative phase shift because we reverse the time for the data. Yeah, zero phase shift. You just run the filter that way, and that's it. Zero phase. Yeah, amplitude, basically, the amplitude response would be, twice the effect. Yeah, so if you have 80 dB attenuation, that will become 160 dB. Yeah, but on the other hand, if you are targeting for, say, 80 dB, then you would have 40 dB and 40 dB stop band attenuation. Works only for post-processing. Okay, so back to the business. So now we have the frequency response like that, and we also had our signal somewhere. Yes, you have a question, yes.
Okay, so if I want to buy this
Mm-hmm.
I must choose something. Two things. The first, I must know the frequency I
Yes.
want to filter,
Mm-hmm.
and I must put the bandwidth.
Yes.
Bandwidth with the value of A.
Yes. Yeah, those two things. Yep. This is good for small systems if you want to reduce the 100 Hertz humming. Works like a charm. Okay, so So now next part would be, well, let's try filtering. So filter, why it doesn't work? Maybe because I wasn't on the right window then. There. So the filter data. So y equals filter PB, AA, and SNON, like that. And let's then listen. Sound of. So this is the original. And this is the filtered. Nothing happened. Why? Oh, yeah. This is not the filter. This is the filtered. Yeah, of course. You know, the third harmonic is there. And yeah, yeah. So here we actually have, well, this is funny tricks our brain actually does. So now we have actually this 440 hertz and the third harmonic, and well, our fine-tuned equipment on head actually recognizes that as a the 440 hertz note, but with different shape of the signal. So it's not sinusoid like flute, but it's closer to a, say, guitar. Guitar has those the third harmonic and fifth harmonic and seventh harmonic quite present. Or violin. Violin is almost triangular shape. The triangular signal generator. So now our the brains are making tricks. So this sounds like it's a higher note. Okay, but anyways, let's do some spectrogram. So I will use in the specgram command. Why? SNON first. So I'm a lazy guy, so I will just do it like that. Oh, shoot. I should actually always. Ah, I hate when that happens. Bigger. That was my. Oh, that one, but the specgram. New figure. There. If I get it to your YouTube. Okay, there. So that's my original signal. 440 hertz and the third harmonic. Yeah, quite clear. Then how about the filtered signal? All right. For, I would guess that we have blue line on the place of the lower yellow line. Yes. There. So that's the difference. Quite efficient. Okay. Small warning. How about if our 440 hertz wasn't 440, but 442? Let me go and take a closer look at my filters. So if you have a very narrow notch, meaning the bandwidth is narrow. Let's see, can I? No, well, MATLAB. I'll do it on the whiteboard. So, uh, think of this one here. If our real frequency is actually somewhere here, it will immediately affect on this attenuation. If it hits exactly the right note, then it's effective. But if it's a little bit off, then it immediately starts to deteriorate this filter quality. But anyway, still, we are talking about second order system, which is very efficient to calculate. And also to tune. So if you had a spectral analyzer on a system which is basically maybe a digital the phase lock loop following what is this the exact frequency, then you could basically make a adaptive filter which follows that this 440 hertz signal plus minus something. But that's again advanced topic, not part of this course. Another way where you actually go easily off this notch is when you have jitter on your sampling clock. If you have 1% jitter, 1% of 8,000 hertz would be already 80 hertz. That's a lot. So our filter was actually 100. Well, the half width was 100 hertz. 80 hertz on that one, it will go to the say 10 dB attenuation only. Okay, you have been warned. Good. So that's the notch filter. Let's take a look at these the other filter design methods and how to design a say classical low pass filter. And these are classic analog filters in digital domain. There's actually a routine, for example, butter, which generates filter coefficients for digital filter. It can also be actually a design tool also for analog filters, although it's a little bit heavy doing it with these tools since there are better tools to do it. Okay, but anyways, you can design a classical Butterworth filter and it gives it on digital domain directly, meaning it does make the bilinear transformation, but it's still analog counterpart. So Butterworth filter, what was special about it, Butterworth? Hi-fi audio. It has flat, optimally flat bandpass response. Chebyshev, what was special about that Chebyshev? It's sharper. Bezel, never use it here. Bezel filter is in analog domain. It gives almost linear phase shift. Guess what happens to that one when you are warping the frequency space? It's totally, destroyed. Yeah, we're losing the linear phase response totally. Okay, then there's elliptic filters which I usually use on these filter banks, that kind of stuff. But anyways, Butterworth and Chebyshev type 1 are the most common ones. Let's see, the Chebyshev 2 is also done. Yeah, but anyways, those are the classical filters. And basically, how you start designing is that you have this filter requirements. Remember the box yesterday? So it starts from the requirement box. Not here, not there. If it's a flat passband response, then basically it's Butterworth. So you give it a -3 dB point. Another point you need to define is the stop and start frequency, and what is the attenuation at that point. Okay, so those FC, FS. This is just for generating the filter coefficients, but there's another function to estimate the order number, okay, which is BUT-ORD. So Butterworth order number. There. N equals BUT-ORD. Wait a minute, how does it go? Minimum filter order of a Butterworth filter desired response characteristics, passband frequency WP, stopband frequency WS, ripple, passband ripple, and RS is the minimum attenuation. Okay, so for Butterworth, the parameters would be, okay, ripple. I think they are asking for where do we define the cutoff frequency. We'll see. Cutoff frequency start, stop and start frequency normalized. Okay, between 0 to Nyquist frequency. So actually our WP is FC divided by Nyquist frequency. Same here, WS is the FS divided by Nyquist frequency. What else? Then the RP -3 dB, and then how much attenuation you want. For example, number for Butterworth type filter with the following coefficients. Stop and start frequency, let's put this one for example at 1 kilohertz. Cutoff frequency 600 hertz. Attenuation say 60 dB on that. No, well, let's be modest. 40 dB, and then the RP is 3. But next part we will change this one to the this normalized frequencies. So our Nyquist frequency is Fs over 2, and now I can do some calculations. WP equals FC divided by Fn. Ws is Fs divided by Fn. Attenuation we use directly, and then 3 dB directly. Okay, so our N, which is the estimate for the order number, butter for order, buttered, WP, WS, repo 3, and this RS is the same as the ATT. Okay, there we go. And this is a number, 9th order. Requires 9th order. Now we can use the Butterworth design and get the BBN and AAN Butterworth. How did it go? Let's see. N and W, yes. So that requires only the N, and then this cutoff frequency would be also, yes, from 0 to 1, 0 to the Nyquist frequency, scaled, normalized frequency, so we can actually put the WP. And those are the filter coefficients. Okay, let me put another figure and check the frequency response. Yes, you have a question? Yes, exactly.
But what is the difference of WN and WP? Is it the same?
Wait a minute. This one gives the also N and WN.
Yes.
Normal 0 to 1. It shouldn't make any difference there. Yeah, it's the same. So let's see. WN. Ah, wait a minute. It's a little bit different.
I don't know.
Yeah, it will be actually shifting the cutoff frequency a little bit. Just a moment. I'll check. Does it give the same stuff for but or no? It's wait a minute. Ah, yes, it actually does. Okay, so it might actually help setting exactly the right frequencies. That's the but odd is just making the estimate, and this is actually the because of the bilinear transformation, you need to a little bit tweak the cutoff frequency. I think it gives the tweaked cutoff frequency, but yeah, better use that one. Maybe. Try it, see the difference. Well, this is not science, this is engineering. All right, so let me do it over again. Okay, N home N and WC was the parameter, but it comes out right. My WC is 1.5004. What is the WP? Okay, there's not that much difference in this one. You have a bigger difference on, yeah. Doesn't know, but we'll use it anyways. Doesn't it give you great confidence, you know? All right, so they're recommending using that one. So it's a little bit tweaked. So I think there's a more if you read the data sheet totally, it might have this some glue what it's giving. All right, but now figure 5 and frequency response of my BBN AAN 1024 NFS. Syntax error. Ah, why did I put there dots instead of commas? Maybe because I cannot see it properly here. Ha! Excellent. C. So 600 hertz cutoff frequency, and then at 1000 hertz I put was it 40 dB? Yep, 40 dB. Yeah, it's about 40 dB on that picture. So it definitely goes by the default. And by the way, when you're doing the bilinear transformation for the these low pass filters, think of the analog filter which has the infinite. When the frequency goes to infinity, then the amplitude response goes to zero. So it always warps like that on these bilinear transformed filters. So that also shows how the frequencies are really warped on these filters. Okay. So, but anyways, we got the filter and now we can actually use it. Let's use it for our data. Okay, YYB BBN. Filter some data. So that's my sound with the harmonic 440 hertz and harmonic and noise, wideband noise. Bah. Sorry. Different. The original. And filtered. So that the hissing sound, which was due to, well, I can actually show it also here. So that's the original. So hissing sound is this white spectral noise on the higher end. And then this is sounds like a little bit like a dark, meaning that this third harmonic is missing. So it was 3 times 440 hertz. So it's 1320 hertz or something like that. That's already on the stop band. But well, we can always, calculate it and see. See figure 6 spectrogram of YYB. There. Makes sense. Right. It was a low pass with the cut frequency at 1 kilohertz, so it doesn't affect on our 440 hertz. But then the third harmonic is already on this downgoing slope, so there's something like 60 dB attenuation, which is enough for us. So human ear, basically the total dynamic range is from around -20 to 100 dB without damage. Well, 100 dB levels for more than 10 minutes can make you deaf. Okay, so below 80 dB. But anyways, dynamic range is about 100 dB total. But when you have, say, in music and that kind of stuff, you can basically reduce anything that is less than 40 dB from the highest, because basically your ear is saturating and these elements are saturating already there. Your brain does not anymore distinguish between different components. That's why you can really compress these music into very small packages, because you can actually get rid of a lot of components there. Anything which is lower than 40 dB from the maximum. Yeah, so that's why we don't actually recognize that third harmonic there at all. Unless if we filter this one with a notch, then we would hear that this third harmonic, but with a faint sound. You have a question? R. Yeah, it will be just different. Okay, let's take a quick look on one of those figures. So we had only 9th degree filter here. So basically we are already getting, something like at the end here, so, or actually we reach the 100 dB stop band attenuation already around, say, 1700 Hertz. So the IIR filters are more cost efficient for this kind of audio processing, since to get a 100 dB attenuation on FIR would take much more time to calculate. It would be higher order. So yeah, so that's the main difference. Since, well, if you do not need linear phase response, then you always get a better, say, more cost-efficient filter by taking an IIR filter. But of course, you can mess it up, but in principle. Okay, so that was the low-pass filter. How to make the high-pass filter? Well, read the manual or the help data sheet. So let's see, help. I think on the but audio already had help on how to make the high-pass design. All right. Yeah, then you can actually do the estimate for high-pass or band-pass or low-pass design for filter, and then you just need to make the corresponding design in here. It's low pass is the default, but high pass, then you can just plug it there, and then there's the band pass or stop band filter. But everything starts from the fact that you need to first do the estimate for the order number. Okay, let's go and take a quick look at today's exercise. What does it actually say? For infinite impulse response systems, band stop notch filter. Okay, so that one. Plotting zeros and poles. Plot first 25 values of impulse response again. And then it's about designing these IIR low pass filters. Okay, sampling rate given, cutoff frequency given, stop band attenuation given, transition bandwidth again given. So basically this is almost the same as on the FIR system, but there's also maximum 2 decibel ripple on passband, meaning that now you should be able to figure out which filter type you would use for that one. There are different possibilities if you take the FDA tool, but basically the two possibilities, simplest ones are the Butterworth and Jeppesen. This one has a ripple, that one has zero ripple. Okay. Minimum order number, meaning you will estimate it with the BUT or Jeb order. Verifying the design from amplitude response graph. Compare. Okay, exactly the same filter actually was designed on the previous exercise, the FIR filter, and you should actually compare what are the major differences between the designs. What is different? Next is the IIR high pass filter. That's good, and then design an IIR filter match the requirements on the 4.7. Oh, okay. That's nice. So you basically would be doing some comparison again. So the same problem. You have the noisy data. You need to figure out what is the speeds there, and do the IIR filter instead of FIR filter. Trying to figure out the language there. It's quite easy actually. Yeah, sure. And then the fun begins. All right, so let me go to the whiteboard again. So since the part 9 and 10 require a little bit of explanation, I started explaining it yesterday. Of course, you will remember it totally. Yeah, sure. That'll happen. So, colors. Where's the, oh, there's the white. There we go. So, so that's basically the 9th exercise is about having this tone adjustment for audio, which means that you would have 3 bands, Nyquist frequency. Low frequencies are actually from 0 to 200 Hertz. Then the mid frequencies are from 200 Hertz to 2 kilohertz. Then the high band would be from 2 kilohertz beyond. On digital filters, for historical reasons, this scale is linear. The frequency scale is linear. But as you remember well from the analog systems, that's not the natural way. So the natural way of actually is the logarithmic frequency scale. So basically, if we have note A at 440 Hertz, then we have the first octave A, is it A1, at 880 Hertz, and then double that one, 760 Hertz is the second. So basically, it's the kind of natural scale for human being in frequency scale is the logarithmic scale. So, but anyways, on digital domain, this is usually on the frequency responses, this is linear. Meaning that actually, let's put it on the perspective. So if this is 20 K here, or 22.05 kilohertz here, then this is 10 K, this is 5, 2 kilohertz is here. 200 hertz is here. Meaning that these bands, this is the bass band. Then you have the middle band. Then you have the high band. They go like that in linear scale. But as I said, this is just, you know, this is bass band. That kind of filters you should do. Filter bank, 3 filters. And then basically you would have adjustment of each of those bands so that you have bass plus 30 dB. Decibels again. Middle band minus 15 dB. And then the high band plus 12 dB. Okay. How to do it? It's your choice what kind of filter you use, either IIR or FIR. You do those filters. Bass. Take the same signal, filter it with high, middle band, and bass band. Then you would have gain of I was plus 12 dB. At amplification, there we have minus 15 dB magnetic amplification, meaning just scaling with the correct number plus 30 dB scaling. And then you would just sum the outputs of each bank, and that is your signal. There. And then you can actually have fun finding some your favorite artist. But remember not to violate the copyright law. So you can sing yourself there and see what happens when you run through it through your filter. Maybe it sounds better. You never know. Okay, so yeah, there's for example, sources like freesound.org, which has free copyright these sound samples you can play with, or you can record with your own. Say, go outside. There are now birds singing, at least on the early morning. So go and record some bird singing, and then or some motorcycles, whatever, sound of silence, sound of humming, ventilators, whatever. I don't care about what is your favorite sound. Okay, so that's the 5th exercise. Before I stop, a friendly reminder. Well, first of all, the deadlines. Deadline of the 5th exercise is on Monday, May 14. But if you get everything done before that one, yeah, I will take a look at those and give the comments and then make the grading. But anyways, on the Monday, May 14, after that, I will, close this course and give you grades, what you deserve. Then about the deadlines, the first exercise deadline is today, You have returned. Have you returned the first exercise? Oh yeah, yeah. You should do it today. You too. You should do it today. First exercise. No, no, no. So basically, we have different deadlines for each of the exercises. You have one. Well, the second exercise deadline is already on Monday. I thought that. Well, yes, you won't have anything else to do this weekend. Not anymore. You don't cancel the parties. So, yep. Sorry about that. I just try to squeeze this one so that the May 14th would be this would be finished. No harm intended. Um, and try to actually do the first exercise return before you leave this lab so that I can check that everything is okay technically. It does not need to be your final answer since this what you are returning is the link to the answer sheet, which means that as long as I have not yet opened that link or started the assessment, you can still make changes. And I will give you a hint. I will not start assessment before Monday. No way. I need my rest too. You don't, but I do. That's one a good reason to study hard and go to the do the needs, do the miles. So, yeah. Any questions? Excellent. Thank you. You have been a wonderful audience. So I will be coming here, also next year probably.